Hello everyone. Today I'm going to talk about the challenges in realizing next generation spectral conversion for enhanced performance of silicon solar cells. My name is Ahmed Gabr. I'm from the University of Ottawa. So we all know that silicon is the most popular commercial solar cells. To date, almost 95% of the photovoltaics are based on silicon. And the maximum theoretical efficiency based on the detailed balance calculations are around 31%. And the world record efficiency is 25%. Here I'm showing a typical external quantum efficiency of a silicon solar cell. As you can see here in the UV blue region, we have the EQ is pretty low, and we have losses here as well as in the infrared region. Something wrong with the equation here, I think because of PowerPoint. Anyways, I'm just showing the relation between the short circuit current and the EQE and photon flux. So for the short circuit current, it's dependent on EQE, and that's why I'm using here the EQE. So in this slide, I'm showing the same EQE. However, I'm showing the photon flux, and the blue curve here is the wasted photons. So these photons are not absorbed by the solar cell in the short and long wavelengths. And in particular, below 450 nanometer, we have 27% of these wasted photons. And above 1050 nanometer, we have almost 22% of these wasted photons. I just want to draw your attention that these percentages are directed for this EQE. So, of course, for every EQE or for a different cell, these numbers will be different. So how can we make use of these wasted photons? And by spectral conversion, and this is the motivation of my talk. So what's a spectral conversion? Spectral conversion is purely an optical process, so it's completely electronically isolated from the solar cell. And this is the beauty of spectral conversion. There is no like intermediate band solar cell, for example, so we will not change the design of the cells. This is completely a layer that can be applied to any commercial solar cell. We have two processes. One is down conversion, also known as quantum cutting, and basically this is converting one high energy photon in the UV blue region to two lower energy photons in the visible region. And then we have like a branch of down conversion, which is called downshifting. It's exactly the same process, except that we have one shifted photon for every absorbed photon. So the maximum efficiency is 100% in this case. And both these layers, whether it's downshifting or down conversion, this is just a layer that is coupled to the solar cell on the front surface of the solar cell. And then we have the opposite process, which is called up conversion, and this is converting two or more low energy photons in the infrared to high energy photon in the visible that can be absorbed by the solar cell, and usually it's located at the rear surface of a bifacial. In this case, it has to be a bifacial solar cell. In my talk, I will focus more in downshifting, but same principle applies to down conversion as well. So what are the requirements for a downshifting layer? So first, we want to have a strong and wide absorption band in the UV blue region, so below 500 nanometer. We want to have emission profile that is narrow, and it's close to the peak of the EQE of the solar cell. We don't want to have any overlapping between the emission and absorption profiles, so there's no reabsorbed photons. Of course, we want to have the maximum optical conversion efficiency, and when I say optical conversion efficiency, I've seen in the literature they call it quantum yield, and this is the efficiency of the layer itself. How many photons are re-emitted in proportion to how many photons are absorbed. And then for downshifting layers, because it's located on the top surface of the solar cell, so some of the re-emitted photons are actually not directed to the solar cell. Some of them escape to the front surface. So I call this loss T-trap, and this just accounts to the number of photons that are going or directed to the solar cell from the total that are re-emitted from the downshifting layer. Of course, we have some total internal reflection that eventually will go down to the solar cell. And this loss is between 50 to 80%. Of course, we want to have high stability of this layer as the lifespan of a solar cell, which is 20 to 25 years. And last but not least, easy to manufacture at low cost. So we want to have very cheap layers that can be applied to any solar cell. So these are the 7 main requirements for a downshifting layer. It's really hard to find a layer or a material that satisfies all these conditions, and that's why until now there's no commercial layers available. So what we do numerical modeling. First I start with MATLAB simulation. So I optimize the thickness of these layers by maximizing the short circuit current. And then I modify the spectrum. So I model the effect of the downshifting layer by modifying the spectrum. I take this modified spectrum into TCAD Centaurus, so it's a semiconductor device simulator, where I have a developed model for different solar cells, and specifically silicon solar cells, and then I shine this modified spectrum to get the IV curves, the short circuit current, and the efficiency of the cell with the modified spectrum. So this is a model for 2D monocrystalline silicon solar cell modeled in TCAD Centaurus. Next, I want to talk about the surface recombination velocity or surface recombination losses in the solar cell. So here I'm showing 3 solar cells with different surface recombination velocity. And as we can see, as the SRV increases, we have lower response in the UV region. And this is the interesting part for the downshifting down conversion, because as we have a poor response at the EPE, this means we have more photons here that can be downshifted to a higher region where the EPE here is maximized. So in this curve here, I'm showing 3 silicon cells. The x-axis is the surface recombination velocity, and the y-axis is the short circuit current. So the red curve here is a control cell or my reference cell. And my reference cell is a silicon solar cell with a downshifting layer that does not absorb. And this is not practical, but I can do this in simulation. And the reason why I did this is that when you add a downshifting layer, you have 2 effects. You have the downshifting effect and you have anti-reflection effect. So you might see an improvement in the solar cell efficiency, but not because of the downshifting effect, but because you have another layer which acts as an anti-reflection coating, and so you have less reflection. So I wanted to decouple these 2 effects, so that's why my control cell here is with a downshifting layer, but does not absorb any photons. And then I have 2 other scenarios here. One is silicon solar cell with downshifting layer. So the green one is I have optical efficiency of 20%, the downshifter, and then the blue one is downshifter with 70%. So it's very interesting here. First, we see that as the SRV increases, as expected, the short circuit current decreases. For a relatively low efficiency downshifting layer, we don't see any, actually we have a negative effect here, and then only when the SRV is around 10 to the 7, we see a positive effect because of adding the downshifting layer. For a relatively efficient downshifting layer, 70%, we see the effect or the positive effect increases as the SRV increases as expected. So, so we know that with a solar cell with a poor response, we expect to get more enhancement. However, what is the required conversion efficiency in order to see this enhancement? So we see two different scenarios with two different conversion efficiency, and the enhancement is different. So what I did is that I'm trying to derive an expression to find what's the minimum required efficiency for a downshifting layer. So first, I derive an expression for the contribution to the GSC from the downshifting layer. So it takes this expression, it takes into account the conversion efficiency of the layer, the absorbance of the layer, which is dependent on the thickness of the layer, the photon, incident photon flux, the PL, so the emission profile of my downshifting layer, and in this case, I'm considering silicon nanocrystals, which has emission between 700 to 900 nanometers. T-trap, which I defined before, it's percentage of the re-emitted photons that are going to the solar cell. And then I have the IQE of my solar cell. And then I have another expression, which is part of this GSC is actually lost. And this is because when I add the downshifting layers, it absorbs some photons that are otherwise absorbed by the solar cell. Although they are absorbed very inefficiently, but they're still absorbed. So we have some loss in the GSC because of the downshifting layer. And in order to see any enhancement, the portion that is added to the GSC has to be greater than the portion that is lost from the GSC. So if we put both equations together, we can derive an expression for the minimum required conversion efficiency of the layer. If we plot this equation, 3D plot, so in this axis here we have the T-trap. I put it as a constant number, although usually it's a wavelength dependent parameter, but here I assume just a constant parameter, range from 50 to 80%. And then this is the emission peak, which is my emission profile. I assume a Gaussian shape profile, and it ranges from 600 to 1,000. And then this is the minimum required efficiency in order to see an enhancement in my solar cell. So as expected, as the T-trap factor increases up to 80%, the minimum required efficiency decreases. And here you can see the optimum point is around here, which corresponds to the maximum of the EQE. So around 1,000 nanometer or around 600, the EQE drops, and that's why here the threshold or the minimum required efficiency increases. And it's interesting to see that at some scenarios you need more than 100% efficiency, and this applicable to the down conversion when we have an efficiency up to 200%, because for each photon, absorbed photon, you have 2 emitted photons. So in conclusion, we saw that downshifting layers, they can enhance solar cells. However, they have to have poor UV response. We have looked at the requirements and the losses in the downshifting layers, and I've derived a general expression that can be applied to any downshifting layer once you know the absorption, the thickness, the T-trap, and the emission profiles. And they can be as well applied to any solar cell, not just silicon. So once you have the IQE and the EQE of the solar cell, you can apply this expression and derive the minimum required efficiency for the downshifting layer. And I would like to thank all the funding agencies for this project. Thank you.